everybody. Let's start, please. It's now 4:30. Good afternoon. My name is Ali Kujuri, for those of you who do not know me. It's a pleasure to have you all here and start the first lecture of the series by Dr. Steve Chen from Keysight Technologies. And generally, I start the first lecture of the series with an expert, invited speaker from before Agilent, now Keysight, to appreciate and acknowledge their support of this lecture series since the start in 2006. And in fact, Dr. Steve Chen has given us the honor to have him as the 100th, believe it or not, lecture of the series since then. All right, give him a hand. You know, he has come with beautiful suit and everything, with eyes and so on.
Sure.
So that's of course. Okay, before we start the lecture, let me make 3 short announcements. First of all, the good news is that we have pizza. We have ordered pizza. It's going to arrive at 5:30. Usually they are sharp, by the way. And then also that right at 6 o'clock after this, we are going to have a class here. So may I ask those of you who are not in the networking class, please, maybe leave the room and so on, so that we can clean up and then do that.
You ain't got to go home, but you got to get out of here.
Now, the next lecture will be on the 17th of September. The title of the talk will be Peeling Atoms via Ultra-Sharp Nanostructure for Biochemical Sensing and Pollution Control by Professor Saif Islam, Electrical and Computer Engineering, University of California, Davis. For our lecture today, Dr. Steve Chen will be talking about the trends and innovation in EDA, that's the electronic design automation software. Dr. Steve Chen is an R&D section manager in the ESOF EDA division at Keysight Technologies. He leads R&D teams at several global sites, responsible for developing simulation software for electronic design, electromagnetic, and electrothermal verification. He is also the R&D leader for the high-speed digital EDA business segment. Steve received his Bachelor of Science degree in Electrical Engineering from South China Institute of Technology and his PhD degree in Electrical Engineering from McMaster University in Canada. He held positions in academia and a small startup before joining Hewlett-Packard in Santa Rosa in 1997. Since then, he has stayed in the ESOF EDA division as the company evolved from HP to Agilent to Keysight. Dr. Chen has broad experience in both academic research with over 60 journal papers published and engineering management. He has technical expertise in electromagnetics, optimization, and statistical analysis, semiconductor modeling, device modeling, and RF microwave circuits and systems. His current focus is on high-speed digital design solutions, particularly on signal and power integrity, electromagnetic compatibility, electromagnetic interference, and photonics. And here is Steve.
Thank you for the introduction. So welcome all to this lecture. Title is Trends and Innovation in Electronic Design Automation Software. So the agenda is, first of all, I'll describe why the need for EDA, or Electronic Design Automation. Then I'll describe some of the macro trends that driving electronic design and the complexity in such designs. And of course, to help the industry cope with such complexity, technical innovations are required to help designers to face up to such challenges. Then I'll discuss the ecosystem and design flows, and I'll summarize with the encouragement for all of you to consider EDA as a possible career choice. Right? So feel free to interrupt me by raising your hand, and I always enjoy not a one-way PowerPoint presentation, but interaction. But depends on the amount of question during the talk. I will leave some room at the end for further Q&A, okay? So let's begin. First, why the need for EDA? In the good old days, when electronic system looking like this, there really isn't much need for design automation. And I don't know, I don't think too many in the room are old enough to actually see things like this, but I am old enough, right? So these are vacuum tube radios, probably in the 50s. So that's even before my era. But this type of circuit with a single transistor and a bunch of resistors, capacitors, and magnets, and a little speaker. In my high school years, I actually construct one of these. And you can go to a store like Radio Shack. Back in China, it's equivalent of Radio Shack. You can buy all these components for $1, a few dimes, and you can actually put this together. Most of the values of these components you can derive by hand on a piece of paper if you know enough sort of circuit basics, right? Resistance, capacitance, what do they do, and so on and so forth. And you can construct a working radio. And really, there isn't any need for computer software to design things like that. But that's not the case today, is it? No. That's an iPad breaking apart to look at the circuitry inside. First of all, you don't see too many transistors exposed on its own. It's all integrated circuits. And here's highlighted, this is the first generation iPad. So today it's even more complex. There are these parts. Each of them is an integrated circuit, a chip of its own from different suppliers. Most of them are actually located in California, the state of innovation. Avago is in San Jose, Skyworks is in Los Angeles, Qualcomm in San Diego, Triquant in Oregon, the list going on and on. Broadcom in Irvine, California. All of these are our customers, and our tool helped them to design these chips. So is that just the story of Apple? No, here's a breakdown of a Samsung Galaxy phone. Almost the same set of supplier, Broadcom, Skyworks, but they had used Intel's chip and some components from Murata, a company in Japan. So I think because Samsung's geographical proximity to Japan, they have a heavier contents. But you can see this is not your grandpa's radio. And you cannot imagine using pen and pencil to derive the parameter values for a design like this. Hence the need for design automation. So let's describe what is EDA. At the heart of EDA is simulation. So what is simulation? The definition of simulation is the imitation of the operation of a real-world system. Okay? And it requires a good model be developed. A model should be able to represent or mimic the key characteristics or behaviors of a component, a subsystem, or a process, right? So that's a simulation. Simulation means you try to mimic the operation of a real system before you actually build it in your computer. And that's a lot cheaper than cut and dry. right? So you can imagine that people in Samsung without software, they would try to throw some stuff together and see if it sticks and works. If it doesn't, well, let's tweaking things around. Well, if with the computer software, you can actually put things around using models and simulate it to see if it works. That's a lot cheaper, faster than cut and try, right? So the word simulation, interestingly, derived from the Latin word similes, or similar. So let's move to the next agenda item. What are the macro trends that are driving electronic design as well as the complexity of such design? So here's a word coined by people in Cisco. We actually took this word from Cisco.com. It's called the zettabyte era. So we probably all heard, if you're an engineering student, megabytes, gigabytes, right? But without peeking at the words, you know what is a zettabyte. Well, the zettabyte is 1 trillion billion byte. A billion byte is a gigabyte. So probably we are familiar. The USB stick I brought with me is 8 gigabytes. You can buy one of those for $12, probably 8 gigabytes. So it's 1 trillion of a gigabyte. And we're not talking about the total amount of information. Cisco is saying we are approaching the day that every day, every second, there's a zettabyte of data traversing the world. So what do all these bytes do? Well, a few things that touches our life, right? Touch our life. One is high definition TV. So today we are probably in most of our places, homes, dorms, so on and so forth. We have an HD or high definition TV. Sorry, the light is quite bright. You may have difficulty seeing the resolution. It's 1920 by, it's about 2000 by 1000, right? That's the resolution. It's already on the market. You probably can go to Costco and buy one for about $2,000 to $3,000. It's so-called the 4K Ultra HD TV. It's about 4,000 by 2,000, roughly twice in its dimension or 4 times the display area or the resolution. Sony is busy working on the next generation, super high, 8K, right? So it's about 8,000 by 4,000, again, doubling or quadruple the space. And the goal is for 2020, Tokyo will host the next Olympics, and Sony by then, the aim is to real-time broadcast all the program in 8K super high HD TV. So you can imagine, you can calculate, those good with math, you can calculate 8,000 by 4,000 pixels of color data transmitting to every person's whatever mobile phone in their hand. How many bytes would it take to transmit that information? And that's only one application. The others, the internet, online gaming, digital home, mobile services, storage networks, and don't forget, high-frequency trading, et cetera, university like this, all consume enormous amount of data bandwidth. You probably also heard buzzwords like the Internet of Things that mean everything we touch are connected by the internet. The lock on your door, your refrigerator, your microwave, your alarm clock, et cetera, your thermostat at home are all connected, Internet of Things. Big data, cloud, all of this is the vision of a connected world in the near future, which will consume that zettabyte of data. Zooming closer, look at what is a computer. So let's walk through the evolution of a computer and our relationship with it. So this is a desktop. We can still see some of those, like one of the there. But remember, as close as mid-90s, 80s and 90s, for about 15 to 18 years, that's all the computers that we have, right? The first PC I bought was in 1983. It's a IBM AT. I was proud of it, paid $20 to $100 for it. It has a hard drive of 20 kilobytes. Imagine that. No, sorry, 20 megabytes. I was wrong. The memory was 64 kilobytes. And when I first heard the word 1 gigabyte, I would say, who needs that data? But anyway, that's a desktop. But as close as 1997, when I first moved to California to work here, this is still the dominant form of a computer that we know. And then we moved to laptops. This dominates in the 2000s, right? Everybody started to switch to a laptop. Closer to today, we have tablets, smartphones, and now wearables. That's a computer, right? Yes?
So it's moving more and more to mobility?
Well, the punchline is here, right? So yeah, so actually there are multiple vector movement. One is the number of users and applications. So desktop is probably hundreds of millions of users, tens of thousands of program runs on it. On the other extreme, there are probably billions of smartphones running millions of apps, right? So the application is wider. Performance, of course, is still higher. But look at the power consumption. Typical desktop and servers can consume up to hundreds of watts, if not thousands of watts, where a wearable like this, they work hard to reduce its power consumption to a watt or less. So the battery can last, right? So that's the spectrum, both in terms of applicability, number of users, and mobility is one of the vectors. So what is, in our view and our life as a computer, has changed. But you can imagine, since the computing power of these are comparable, to get something that used to take the form factor of a desktop to something this small, what does that mean? Increased complexity and the challenge to get it to work properly. Now look at phones. I dare to say everybody got a mobile phone, right? I mean, you probably don't have a landline, but you have a mobile phone. The first generation mobile phone is voice only. It's an analog phone. It's probably one of the flip phone or something like that. And then we had 2G or GSM phones that can support SMS text messaging. And you can count this. This is probably 1993, 94. We start to have mobile phones. And text messaging is probably 97, 92, close to the millennium. And then we moved to 3G phone, where you can actually see some kind of internet connection. Smartphones start to take place. Right now, the dominant form in developing countries is 3G. In Western countries, it's 4G. In Japan, you can't even get 3G support anymore. All Japan phones are 4G or better, right? So that means very good connection. What we are working on is 5G. 10,000 times more capable, blah, blah, blah. You don't need to worry about the detailed statistic, but this is still evolving. And many big companies, and if you do apply for a job, whichever high-tech company you work for, probably this is one of the buzzwords you'll hear, 5G. Cars used to be a rolling piece of mechanical box on 4 wheels. Today, it's more like a computer or a farm of computers on 4 wheels. If you dare to break a car apart and count the computers in it, it's astounding how many computers, right? So it has its own requirement. It needs to be super reliable. You can't have a car in the middle of a freeway wanting to reboot itself, right? Et cetera, et cetera. So reliability, and it's an amazing piece of engineering. I always admire automotive industry. Right? The car needs to be on a really bumpy road for years and years, traveling at nearly 100 miles per hour if the police allow you to do so, right? And reliably doing so without blue screening on you or anything like that. Right? So that's pretty amazing. And where we work, we also provide software to help handling and designing these type of systems. Oops. So the next one is enough about complexity and macro trends. So in order to cope with the complexity, we need technical innovations. So innovation is a good thing, correct? Yes. But usually innovation, unintended, is also bring on challenges. Right? So we'll look at them in pairs to see how that happens. One is we need memory storage for this zettabytes of big data. All the pictures you took using your iPhone or Android phone or digital SLR camera has to be stored somewhere, right? You said, oh, don't worry, I just store in the cloud. But someone has to provide that storage space for you to store that data. So there's all kinds of schemes to come up with memories. And memory storage capacity is only one of the factors. The other factor is the speed with which you can retrieve the memory from the storage. Do you know what is the bottleneck of most computers today? It's not the CPU. It's not even the memory capacity. The gating factor often is the speed with which the CPU can retrieve the data from the memory, right? You can imagine that, I don't know what's your major, but if you probably have a loose idea or rough idea of how computer memory work, right? So it's somewhere there's a little piece of silicon that can be flip and flop, 0, 1. So if you have a 8 gigabyte memory, so it's somewhere in this universe, if you zoom it up, there's a bit that's flipped, and you need to access it. So imagine there's a city, a house in a city. So you need an address. So as the city gets bigger, so it's probably easy to find in a little town like Kotati, a house, right? Even if you don't have a map, you can probably, by wandering in long enough, you'll find it. In Santa Rosa, it's harder. In Los Angeles, it's probably next to impossible. In New York City, well, so you imagine that, right? But New York City doesn't have 1 billion people. When 8 gigabytes, that means what? 8 billion bits, and you need to find it. And the ability to retrieve such bit on demand at the instant is a big challenge, the so-called memory bandwidth. So there's a lot of effort going to high bandwidth memory as well high capacity. So, but you need to move that data not just between the memory and your CPU. You need to move the data from one place to the other, from some cloud somewhere in Amazon cloud server to somewhere else, right? So when you log on to, I don't know, some digital library online, and you click on an article to read, well, that data got to be moved across long distance. So that's a challenge to moving that data. So refresh your memory. Again, some of these is probably you never heard of. What is a dial-up modem? Well, we used to have that. It's a gadget hooked up to your phone line, and when you in your computer, you click it, and then finally, hopefully, you make the connection. And its ability is to transmit 56 kilobit per second, and that was considered pretty good. Good enough for email. Definitely not good enough for any graphics, trust me. So then we move to DSL, and start with maybe 500 kilobit per second, 1 megabit. Currently, the best DSL is close to 10 megabit, but there's a theoretical limit to DSL. The highest is 8 some megabit per second. You can't get past that. The next better is cable modem. But the corporate intranet, like if you work in Keysight in our office, the trunk line come to your desk, it can carry 1 gigabit per second. That's a typical corporate intranet speed, right? But that's only intranet, so we go to the trunk line to carry the data from city to city. The current generation is about 20 gigabit per second. The next generation is 100 to 400 gigabit per second. And then they make these lines run in parallel, right? So then that's how carry this data. This is a kind of ugly picture, right? There's a data center. Each of these cubes is a blade server. It's a computer that's no display, just basically a CPU with memory. And you plug into one of these cubes, and there are tons of them. And they are connected using either copper or optical cables. So how would you like a job pacing up and down this aisle to find which one is broken and replace it? Not me. Oops. Well, fortunately, that's only a slide. Wouldn't you hate it if your computer actually gave you this? And all of us have seen this, right? It's one thing that it happened to your laptop or to your iPhone. It's another thing when blue screen happened to a corporate server. Imagine Wells Fargo server has a blue screen. That's a big problem, right? In the middle of a trading day, New York Stock Exchange has a blue screen. That's not a good thing. And actually, there's an article, a very recent information, that corporate America are losing as much as $100 million a year because their server went down. So reliability is important. Now, a quiz, in case anybody want to know. When your iPhone or your iPad or your Android phone got frozen, and you need to literally power it off and power it back on, what was wrong with it? Was actually the memory circuitry broken, defective? No, because if it is, you couldn't bring it back up, right? If literally the CPU, if the chip is really broken, you can't reboot it. The reason you reboot it is somewhere these 0 and 1s got jumbled up. And the computer got confused. They read an instruction it couldn't decode. And it got kind of paralyzed. And therefore a reboot basically cleared out the pipes. And then you can back to operation. So server down is not a hardware reliability problem. The chip can very well be perfect. It's the transmission of this 0 and 1 and the deciphering of it is subject either something went wrong or just a interference from, static or something, right? Yes?
Why does it happen more often when your phone is older?
Yeah, so sometimes the hardware, a bad connection, the wear and tear could play a role. So that's true. And there are occasionally it's beyond repair, right? Your computer went blue screen and you reboot it and it just dead. That means it's a real hardware failure, right? But more often than not, it's rebooting. In fact, I was talking to Qualcomm and they were saying their chips are more expensive than cheaper knockoff from, say, China. So I was asking them, why do people pay for your chip when they can buy for 1/3 of the price from China? They say, well, if your phone constantly need to be rebooting, he said, if you buy a cheap iPad knockoff from China, I bet that you need to reboot it several times a week. And the reason why is because they don't go through as rigorous testing for the reliability. So we talk about what? Storing the big data, transmitting the big data, but at the end of the day, for the data to serve us, we need to make use of it. That means we need a computer processor closer to us to process data and tell us something useful, right? Process a bunch of 0 and 1s and show a picture to us or news item. So how many category of integrated circuits are there? Because integrated circuits is really the backbone of the digital age. So one of them is called ASIC. And I purposely introduced these acronyms because in your future, in industry, you're going to run into these acronyms. ASIC means an application-specific IC. Means somebody built a circuit for a specific purpose. It could be a CPU for your Intel laptop, right? That's a specific one. It could be a chip built in Taiwan for Bluetooth, for Wi-Fi, for USB, etc. It's expensive, very expensive. To take one of these takes millions of dollars of upfront capital investment. So you don't change the design very often. So how are you going to cope with it? Clever people come up with this second concept called FPGA, or Field Programmable Gate Array. Basically, it's a blank sheet of paper with lots of silicon gates or transistor in it. And it's designed such a way that after it's shipped, you can program this chip to do whatever you want it to do, right? So it's less efficient than ASIC, but it's much more flexible. And the beauty of it is after it's installed in a phone, you can still reprogram it. That's why sometimes we say they go into iOS upgrade and magically your phone suddenly can do new things. More than likely, they reprogram the FPGA to do something different. Last but not least, one chip is not sufficient, so they put multiple chips into a little thing called a module, and that's another trick. In fact, in Keysight, one of our powerful tools is to help customer to design such multiple technology, multiple chip module. It's not the easiest thing to do. Another sort of informative slide about the relentless increase of circuit density. So here's the state of the art currently. Most of the foundries in the world are shipping. If you get into the industry, you'll hear things like 16 nanometer, 14 nanometer. So I'm trying to help you to see what those things are. So most of these cutting-edge foundry are shipping stuff in the teens of nanometers. So what does that mean? Okay, so here's an IBM roadmap about how things evolve. But just to give you an idea, a nanometer is 1/1000th of a micrometer. A micrometer is about the size of a copier, toner, cartridge particle. So if you have a Xerox machine and the black stuff spill out on the floor, those tiny little particles, each of them putting under a microscope, measure 1 micrometer or 1,000 nanometers. A smaller particle, a campfire smoke, which is so light, it can actually woof off into the air, is about the size 1/10, 130 nanometers. So today's cutting edge microchip, so these are measuring the dimension of a transistor on silicon. So today the cutting edge is 1/10 of the diameter of a campfire smoke particle. Can you imagine that? So that's why when you hear Intel operating clean room, do you know why they need clean room? You are covered from head to toe because a sneeze or even a dandruff particle that falling out of your hair could destroy a chip completely, right? Because it's multiple size of a transistor. One particle, invisible to naked eye, fall on the chip is ruined. Okay? Now, of course, today we are pushing towards a 10 nanometer. The interesting thing is the size of a silicon atom is about 0.2 nanometers. So you can do the math. That means one transistor is approximately 50 atoms across. 50 atoms. So when someone says we need to count atoms, they are not joking in this context. So if you miss your fabrication technology, misses 2 atoms that have a material impact on the quality of your integrated circuits. So the art of hardware and software and technology to go into make such design reliable is nothing short of a miracle, remarkable for the creativity of engineering. So you should be proud that you are in engineering. One day you might be pushing the envelope beyond this. And electronics is no longer sufficient. People are start looking into, instead of transmitting information by electrons, to look to transmit it using light or photonics. And there are advantages of transmitting light. Like this is a laser pointer, right? Light has the advantage of very little loss because its directivity is extremely good, especially for pure light like laser, which is a single kind of light, right? That's why people can shine a laser all the way up in the air into the cockpit of a jumbo jet. And it doesn't really go from, it's still a very little dot, right? Electron, no such luck. If you have a spark of electrons like a lightning, the electrons are dispersed easily, right? Widespread. So optics are the future of transmitting information. But to design things in optical is difficult. Enough? Your head is filled with information, and now you realize, say, maybe I regret getting into this business. So much easier if I just, in finance or accounting, at least I know what I'm talking about. All of this stuff, how am I ever going to learn enough to be successful? Right? Any questions so far? No? Yes?
So on the optical transmission, I've heard one of the problems is designing kind of the equivalent of a flip-flop, but for light, capturing the state of light, having a 1 or a 0. Have you guys done anything with that?
Yeah, optical storage is a totally greenfield research. that's really hard. Yeah. To first of all, for electron, when you flip you can have it retained for a long time. Optical, I read article about it. I don't know. And IBM, I think they say they have some prototype, but I'm not aware of any, industrial scale deployment of optical storage. Yes.
So when they're doing that, or the question of optical is, so they're just putting fibers on the chip too? Does that create another kind of challenge there on
Yeah.
how small you can make those?
Yeah, so usually the trick is, the other term is called EOE, or electrical, optical, and electrical. So they only use the fiber optic as a means of transmitting. So what happens is you have electronic is still where on one end of it is still all electronics, right? So they generate the signal, but before they transmit, let's take an example like cable TV or something, right? Internet. So on one end it's electronic. Then how do they convert electronic into optical? They use a laser. So they use electricity to modulate the laser. So the laser literally just beaming on and off for 0 and 1, right? So 0 means off, 1 means it's like a blinking beacon. So this transmitted to a fiber optics for how far you need it to go. On the other end, you need the reverse of the process. So there's such a thing called a photodiode, which can convert light, or the absence of light, into a series of electronic pulses. Okay, so the catchword is called EOE, electrical, optical, electrical system. At the end, it's still electrical, but in the middle, they take advantage of the efficiency of optical transmission. Yes?
So the problem is trying to actually store light.
So they avoid that problem by this way, right? Because it's storage and processing is all in electrical domain,
But that's
only the transmission in optical. But one day, the question was, if we figure out how to
store.
build the reliable devices to store light in optical form, then store photons, stay in one place and don't flip around. Maybe it can be more efficient too. That's yet for you to discover. All right, let's move on. So now bring it closer to home. So what do we, Keysight and myself, contribute to the betterment of the art of science and innovation? So yes, we provide simulation. So we all talk about what simulation is, right? Simulation, the imitation of a physical, real-life system using, computer code in virtual world. And measurement, that means actually measure the real thing. So we provide solutions in simulation and measurement across the spectrum of design. So first of all, start with components. That means the little things like this, or integrated circuits. Then we put these components, assemble them, called a module. And then we put these multiple of these modules onto something called a printed circuit board. You probably, if you have a computer, you take it off, you will see one of these, right? It's a little thin board with stuff on it, and you plug it in, right? That's a board. And then when multiple boards go in, you have a system. And then there's the end of it is two systems. In the middle is some kind of transmission facility. This could be copper, it could be fiber optics, or it could be completely wireless. So there are three basically multiple means of this type of transmission. So we provide solutions in simulation and management for all of this. Okay. Who in the world are our customers and making parts or the whole of these systems? Let's review. So here's an ecosystem, right? So at the beginning, you need to make the semiconductor or silicon chip. And sadly to say that it's so expensive that US decided we're not going to waste our time doing that. So it's mostly existing in Asia now, right? So all these big names, TSMC is in Taiwan, Win Semiconductor is in Taiwan. Japan used to be in this game. They got out of it also. US still have some capability. IBM, for instance, there's a Jazz in Southern California. We retain some of the capability because aerospace defense would not use components made overseas. So IBM exists to serve the need for the Department of Defense. But most of consumer electronics, the chips are not coming from the US. It's from Taiwan, Korea, China. And then these chips are going into more complicated design, and these are US companies. Intel, Qorvo, Triquant, and so on and so forth. And some European company like NXP, and then we put chips into a module into a board, and that is Motorola, Qualcomm, or they go into another form, Skyworks. There are companies that making discrete capacitors, inductors, and typically these are Japanese companies like Murata, Toshiba, so on and so forth. Eventually, things come together into what we call a system integrator. So these are the people that made actual product. It could be Samsung, could be Apple, it could be HP, right? It could be Dell that produce computers, okay? And people making antennas and so on and so forth. So that's the ecosystem. And let's just put a name into some of these companies, and all of these are Keysight customers. Second, if you are a designer, what exactly do you do to turn something from the beginning to an end? So many, many things you need to do. So here's designer, right? So first of all, you need to create a model. Remember, for simulation to be successful, you need model. So people creating, so let's follow the blue line first, and then we'll come to the what do you call, orange or yellow line. The blue line, you start to create models. Then you're using one of our tools for simulation. And then you do, making into looking more real, what they call layout. So the difference here is you represent, say, a resistor by a symbol. But a real resistor doesn't look like the symbol, right? The symbol is usually a little rectangle. But a real resistor doesn't look like that. So at some point, you need to transfer from the symbol into something that look real. And that's the process called layout. Once you lay out, you do some more simulation, and then you actually produce a prototype. A prototype comes back into some measurement, see if it's good, you are done. If it's not, you go back and find out what's wrong with it, and you iterate. So that's what the design. Now, this is no single designer does all this. This is a company, and usually they divide up into little groups to do various stages. So the key for a successful company like ours is you need to provide tools for every single touch point of these people, right? If you only supply part of the tools, they're not going to be satisfied. And what did I say, EDA? So quiz now. What does the A in EDA stand for? Automation. So automating what?
Design.
Yeah, and automating the transfer of data throughout this cycle. People often overlook that, right? So I work with enough engineers that create a really cool tool to do one of these, but they didn't give enough thought about how does the data get out, right? So imagine that you have a really good word processing program like Microsoft Word, but you have one that's better than Word. But oops, you forgot to allow it to print, right? So this is super. It makes sure you use all the right words and spelling and super fast. It reads your mind, it reads your eye, blah, blah, blah. But it can't print. Oops, right? Or you can't email it. Well, that's not good. So that's the thing. Automation is as much to do about automating a task as automating the continuity of these tasks. That's why I use the word design flow, because we find many designers spend more time walking the stuff between this than actually doing the task itself. And in between tasks is where most errors happen. So here's what we do. We do system level, component level, and physical level simulation and measurement. Let me walk you through a little bit more about the challenges. One of the challenges is when the circuit gets very high density, even the physical design of it is very difficult. Here's an example. Here's a chip made by one of our customers. The size of the chip is 3 centimeter by 3 centimeter. Now on a slide, because it's a projection, I could never guarantee that it's the actual size, so I put a quarter as a reference. So 3 by 3 centimeter is roughly the circumference of a quarter. So take out the quarter from a pocket to visualize how big that chip is. That little chip has 500 pins you need to make connection to. So your job, maybe one day, is make it successful. Make reliable connection to these 500 pins. So that's what this thing's doing, right? It's not that easy. It sounds trivial. I'm not even designing a chip. Just try to make connection to it. Okay. Challenge in modeling. Nah, not this kind of modeling. I'm sorry. This modeling. Right? So device and circuit modeling. So there are a variety of models. And by the way, I made available the material in PDF forms to professors. So you don't, if you don't want to, you don't need to take any notes. You could ask for a copy. You can read the detail. Okay, yeah, it'll be good. So there's a variety of different models, from a compact model, which is based on empirical and heuristics, to a database model, to table lookup model. The most advanced is so-called self-learning model. That is the art of modeling, right? You try to create a model that mimics how our brain works, neural network. By observation and experience, you can self-correcting and so on and so forth. Quite powerful. By the end, the challenge is a never-ending pursuit for speed, accuracy, and scalability. Let me just touch on that. The simple model have high performance, right? We know simplicity equals speed, right? But then it's usually less accurate. An accurate model can be super complicated, so it's slow. And a complicated model may not be scalable. It works for one thing, but doesn't work if it just have a little change. So that's the struggle for engineers. And system is never perfect. So system has imperfection. And in our simulation, we must not just simulate the ideal or the expected behavior. Just as importantly, we need to be able to simulate the imperfection of the system. What are some of those? For instance, two of them notorious is electromagnetic compatibility, or EMC. The converse of it is electromagnetic interference, or EMI. Now, EMC, if you buy any electronic device, you often puzzle over the little user's manual or guarantee that says, in compliance with government regulations, so on and so forth. And in Canada, it complies with this. In Europe, it complies with this. What are those regulations governing the EMC? In other words, does this device transmit waves, propagations that can interfere with other devices? And you have to test that. You have to guarantee that you won't. Because some poorly made cordless phones would interfere with your TV, right? Some of you might heard about it or even experienced it. So EMC is very important. The converse is EMI, meaning how good your device is able to withstand some of these interference and so on. So we need to be able to simulate such impairment. And one powerful way to simulate the imperfection is to going back to the first principles. Okay, so what does that mean? A model, again, go back to model. How do we model a simplest one? Resistor. Probably all of you taking some physics, right? Electronics. So what's a resistor? Resistor, the simplest formula is resistor equal to what? Voltage divided by current, right? Okay, so that's resistance, that's the definition, but that's only idealization. In real world, nothing is that simple. So instead of using that simple formula, you can go back to the original physics equations. One of the fundamental set is called the Maxwell's equations. And it said that if you solve everything based on Maxwell's equation, it's as good as gold, right? It's the real thing. So we created a whole bunch of simulators based on exactly on those first principles. And you can see that these are not simulation using some kind of a symbol. These are simulations using what look like the real thing. in 3 dimensions, right? And usually the color coding gives you some idea about intensity of some kind, high current, high temperature, low temperature, high voltage, low voltage. And designers really appreciate this. When things work nicely, they don't care. When things don't work, like your phone, after a while, have smoke coming out of it, that's not good. So the engineer will want to know where things got heated. So a simulator can help you see that. Electro-thermal simulation is, again, another simulator going back to first principles. The other challenge is, at the end of the day, simulation, as good it is not the end. It's a means to an end, right? Some of my engineers forget about it. They say, voila, successful. I just say, how come? Because the simulator says this system works. Okay, the computer says it works. Does it actually work? To the surprise of many, novice engineers, the computer says it works. When you actually build the thing, it doesn't work. Okay, so that's illustrated here, right? The divided world, the virtual and the real world. And in Keysight, we produce tool for this path as well for this path. So one of our challenge is to try to create some kind of coherency between these two, to allow engineers to map the virtual and the real world. And when things don't agree, have a way to find out why they don't agree. Maybe the model are not accurate. Maybe the simulation methodology has making some assumptions that simplification, et cetera, okay? So an analogy that you can all appreciate will be computer simulation of trading stocks. So you're trading stocks, say, I am a millionaire. I'm so good at trading stocks. And then you went on the real world and maybe it's not so good, right? So reality at the end, building stuff, measure it, making sure it works, is the real job. Simulation is an aid. Okay. So here comes to the last part. I think I only have 2 slides left. This is the second to the last, so relax. I'm not going to go over time. As I've been saying, one of my objectives is to encourage you to consider a career in this field. So what would it take to get a job in this field? I say it's pretty demanding, but at the same time, it's very exciting if you qualify for it. So it takes knowledge, some level of knowledge of electrical engineering, right? Because so far, all we talk about the electronic design automation. So if you don't know anything about electrical engineering, if you say, what is a voltage and what is a capacitor, well, maybe this is not for you. Okay, so you do need that electrical engineering knowledge. Is that sufficient? No. You need math. Oh, I hate math. No, you need to be good at it. Because remember, simulation is an effort to mimic the real world. And how to do that is you need to create really cool algorithms, formulas to model and to simulate the real world. So math is a fundamental differentiator between you and your coworkers. If you are a basic engineer, you know 1 + 1 = 2, and that's about it, you're not going to get very far. You may be relegated to some job that just kind of punching in something, right? Not very creative. The one that really good at is they are really solid in math. But I'm not talking about theoretical number theory, that kind of math. I'm talking about applied mathematics, right? Differential equations is important, but algorithms, how to solve, how to invert a matrix, LU decomposition, that kind of numerical analysis, basically. 2, but last but not least, you need to be a really good computer programmer. We are talking about software, right? So you need to be able to create software. And I mean more than just be able to write some Python script or say, I know how to write a few lines of Java code, pretty good. Yeah, that's good, but you need to learn some fundamentals of software engineering or programming. If you got all these 3, and I don't mean you need to be perfect in 3. Such a person either doesn't exist or If they do, they don't work anywhere I can afford them. So a suitable combination, and it's all a matter of balance, right? So you need to be very strong in one of these three, but you need to have some knowledge in the other two. That I have jobs for whatever leaning it is. If you are really good at math, not so good in programming, sure, I'll ask you to work out, the algorithms and to crack formulas and so on and so forth. If you are really good in programming, little less on math, fine. You can take the formula from the math guy and turn them into high-performing, robust computer code, right? Et cetera, et cetera. So if you are possessing a combination of these skills, you could have a wonderful career in EDA software. Now let's put it in words. Core skills: electronics, circuits and systems, semiconductor physics. Don't mean all of it, some of it. Software, programming, math, algorithms, user interface, usability. Last, a non-technical soft skill, which is fundamental for you to be successful in any endeavor of your career as an engineer: curiosity, creativity, and communication. You need to be curious. If you're not curious, no good. I have guys that come in every day, go into their own cube. They don't attend other people's talk. They certainly don't come to talk like this. Why? They say, I know everything I need to know to do this job. Well, you know what? The rest of his life, that's his job, right? Curious. Asking people, like, questions. And can you store data in optics? So on and so forth, right? Those are good questions. Curiosity. Wondering what other people's doing. And then be creative. Think things that out of the box, as the cliche goes. Lastly, you need to be able to communicate ideas to your boss, to your coworkers, to your customers, to future students, right? If I'm not good at communication, I would have wasted an hour of your time, right? And you regret it greatly that, that's an hour I never get back. But if I'm good at it, well, you learn something from an hour. That's the end of my presentation. Okay, we did have a few questions during the talk, but now we have 5 minutes. Questions? Usually I'm so good at it, at the end there's no question.
No, you are.
No, really, yes.
So the question I have is, in terms of one of the biggest challenges that your engineers have, what would that be?
Well, complexity. So
Complexity.
we are getting to a place that we used to, there will be a principal engineer in any sort of company or department that is knowledgeable enough about all they do, and he's able to supervise, he or she supervise the entire thing or shepherd it technically. That has become nearly impossible. No one really is deep enough or broad enough to know everything. From electronics to optical to semiconductor physics to electromagnetics to thermal. How? So that's the challenge. Yes?
So do you think that increased specialization slows down progress, though, as well?
Yeah, so I
mean,
think
is
that,
there, because you were talking about, like, even for what you were just saying, for that you needed to have these 3 different skills, but you could be really good at one, but you still needed the other 2. So, but what you're also saying now is that you need this specialty in order to handle the complexity. So how does that?
yeah, so it takes teamwork is the magic, right? So there will be need someone who's broad, but not necessarily deep, like me. So I used to be a really good engineer. I was hand-on, I write computer code and so on, right? I rise from the technical rank, and as introductions, I published 60 journal paper. The last publication is probably 12 years ago. I haven't published anything because I couldn't afford to go deep. But I go broad instead. So you can see I could talk until the cows come home on many, many topics. But obviously, it's enough for this class. But if you are a specialist in the field and you keep drilling me, at some point I'll just run off. I say, I really don't know. Go talk to one of my engineers. So the job of someone like me is to coordinate and to lead a team of specialists, right? But I always encourage them to be curious. So they don't need to be as broadly knowledgeable as me, but they need to curious enough to know what their coworkers are doing. Otherwise, we have problems. Yes?
So do you encourage engineers to do more schooling, like after undergraduate, to be special before?
No amount of schooling is enough. To be honest, education in all the way to PhD is really one thing, teach you how to learn. That's it. And when we hire people, to be honest, I do care about what you know, but only to some extent. What I read, because I know what you already learned is going to be out of date in a few years. It's the ability. You know, look at the computers. If you are a specialist in desktop, and that's all you know, you're going to be out of a job soon. But so your ability to learn is the key, right? So and schooling, the reason graduate school is something, you know, for you to consider is it challenges independent thinking, right? In undergraduate, mostly you still sit, listen to lectures, get assignment, ace your tests, you're done. When you move up to graduate school, I remember the first day in my PhD program, I saw my supervisor was saying, so what should I do for my PhD? You know, I was thinking like undergraduate, your professor would say, here's the assignment. Finish this, get A, and you have a PhD. He says, oh, these are the interesting topics. Go to the library, see where you can make a contribution. I say, oh, I'm in trouble. But that training educate me how to learn. Given the challenge and topic like I described, challenges, problems we face, I'm not going to be able to tell you how to solve the problem, right? Your value is by independent research, learning, standing on the shoulders of giants, as they say, find a new way to do things. And education kind of enable you to do that. One last question? Yes.
What programming languages do you use?
C, C++ are the most common. In Keysight, we're using C# for instruments. And we do use Python and other scripting language for customization. And we use MATLAB scripts for post-processing, you know, some of this. But the core of compiled software is C and C++. All right, thank you for your attention.
I would like to thank Dr. Chen for his really excellent and attractive